All right, so with degree 3 polynomials, we get the picture of that going on. There, it's similar to a linear polynomial or a degree 1 polynomial in that you've got one end going one direction, the other end going the other. That's an important relationship to think about. That cubic and linear are similar in the way that the directions that they go. Okay. What would be the slope of that picture for the linear? What kind of slope is my blue line there? A positive slope. On the degree 3 polynomial, the leading coefficient I can tell is positive because the line is going in that same direction like a positive slope would be. If it had a negative leading coefficient, it would go in the direction that a negative slope goes in. Okay, so that tie together between the degree 1 and a degree 3, if you'll start tying that together, it's going to help you as we go through this whole chapter with that stuff. So knowing those things. When you look at degree 4 polynomial, it's just taking it and adding an extra term to the degree 3, and you got this leading coefficient in front of an x to the 4th power. Okay. The 4th degree polynomials, the word that's used to be used a lot was quartic, but nobody says that stuff anymore. They just call it a 4th degree polynomial. That's what I'll call it. But quartic is the word, so if you want to Google it, you can. But most of the time, most textbooks say 4th degree polynomial now. But the older mathematicians back 100 years ago called them quartics. That's just redundant. With a 4th degree polynomial, you get all of the same stuff happening as with a quadratic or a degree 2. Notice how the degree 2, the one I drew was a one that had a positive leading coefficient, so it opened upward. Well, the 4th degree still opens, both ends go in the same direction like the x squared graph did, but it's got a few turns in between. Now you can have that little W looking shape kind of to it. So depending on all the other coefficients in front of x cubed and x squared and plane x, how many of those terms happen. But the idea here is that squared and 4th degree, or 2nd degree and 4th degree, look kind of similar. They do the same kind of things in behavior-wise. And then 1st and 3rd degree do kind of the same thing. That extends further if you go 5th degree. 5th degree is like 3rd degree and 1st degree. 6th degree is like 2nd degree and 4th degree. So odds act the same way, evens act the same way when you talk about degree. Okay, so that's something that you might want to note, is that odd degrees and even degrees act in similar ways as far as directions and in behavior. Okay? Odd degree and even degree, as far as in behavior goes, you can think about the most basic one. The most basic odd degree we have is a linear. The most basic even degree we have is quadratic. Those are two things we really know a lot about already. Okay, so if you remember those things, 4th degree and 3rd degree do the same things. 5th degree does the same things. 17th degree does the same things that a 1st degree does, as far as directions of the end behavior goes. Okay, 22nd degree does the same things that a quadratic does, as far as end behavior goes. Okay, a lot of twists and turns in between, but the end behavior does a similar thing. So that's something that you got to keep in mind as we go here. We're going to look at the graphs of a polynomial here. This one is not in standard form, so we're going to look at the graph of that. We're just going to look at it with the graphing calculator. I'm not going to draw it by hand out of this, but there's some things going on here that are fairly important. Before we graph it, let's talk about the degree of that polynomial. What would the degree of this polynomial be? X to the 4th power. So 4th degree polynomial. So what do we know about the leading coefficient of that thing? What would be the number in front of x to the 4th if we multiply this all out? The 1/2, that number that's in front. right? So that's a positive number. So even degree, positive leading coefficient, what do both ends of this one do? They both point up. There's a lot of stuff going on in between, but both ends go up. If it were a negative leading coefficient, if that were a negative 1/2 in the front, both ends would go down. There's a lot of stuff going on in between, but the idea here is to be able to look at the degree and the leading coefficient and be able to tell what the ends are doing without doing anything, without having to graph it or anything like that. You just know that information. So let's look at the graph of that. So I'm going to type that in just like it is in the y equals menu. So clear out anything else you got in y equals. Make sure your stat plots are turned off. So if you've got a plot, if you go to y equals and you've got a plot that's darkened in like that, you need to press the up arrow and hit enter to turn that off. And then go to the y1 and type in your 1/2 parentheses x minus 1 parentheses x plus 3 raised to the second power. Whoops, wrong arrow. Go up. And then the last one is parentheses x minus 4. All right. We can't see the entire graph here, but we do see some important things happening here. What are the important points that we can see on the graph right now? The x-intercepts. Remember when we were doing everything we've done throughout the whole semester, we talked about important places on graphs, and x and y-intercepts were those things, or were two of the important things that we found here. So we got an x-intercept over here at -3. We got an x-intercept at +1 and +4, looks like. All right. So where's that coming from as far as our polynomial goes? It's when you set everything that's in parentheses equal to 0. So this is like the intercept form of a quadratic, right? But it's a 4th degree. So we got it in factored form. We can find all those x-intercepts real easy. What is interesting about the x plus 3?
It's squared.
It's squared. So it counts twice, right? And when we look at the graph, what's it doing at the x-axis there? Bouncing off. Y'all remember this from Algebra 2? We talked about all this stuff in Algebra 2. It's the same stuff. Just talking about it in college algebra again. All right, and our notation's a little bit different in here. We don't do a little bit more collegiate notation with that, but it's the same stuff. Okay, so all of those things are happening. We know that both ends are going up because it had a positive leading coefficient and it was an even degree. Okay, if I zoomed out, maybe I could see the picture a little bit better. All together, we see that W kind of looking shape with x to the 4th power out of that. So you can see the whole picture happening there. But we're mainly just looking for general shape of that graph and talking about end behavior and stuff like that. All right. So knowing degree, leading coefficient kind of ideas as far as the graph goes, and knowing things about intercepts when it's in factored form. Let's bring back something else from good old chapter 3. Those transformations that we talked about. And when you talk about those transformations, you got to remember if it happens on the inside, what kind of shift is it? Horizontal. Outside is vertical. And then the multipliers on the outside do what?
Up or down.
Not move, stretch it or compress it up or down. Multipliers on the inside do the horizontal stretch and compress. What does this one do? What's the transformation? Without graphing it with the calculator, what's the transformations that are happening here? Left 1. Down 4. And a vertical stretch by a factor of 2. Good. That's exactly what that's doing. Go back and review yourself on those transformations. It comes back up again in this section, okay, in this chapter. We're never going to, we're dealing with polynomials. We're not going to depart away from all the things we already know about functions and polynomials in general. Okay, that's all we're after on that problem. Now, this relates back to example F. Describe the zeros of this polynomial. So what are zeros? What's another name for zeros? X-intercepts. All right, zeros and x-intercepts are the same thing. If I said solutions, that's the same thing. Okay, x-intercepts, zeros, roots is another name for that. That's kind of the older word, but it's still used some now. So if it says roots, zeros, or x-intercepts, those are all the same things. Okay, how do we find zeros, roots, x-intercepts for a polynomial that's in factor form? Set each factor equal to 0. That's right. So everything that's in parentheses. So x minus 2 equals 0. X plus 4 equals 0. 2x minus 3 equals 0. Okay. So when you solve those, you get x equals 2, x equals negative 4, and x equals 3 over 2. But there's a little bit more information that goes with that because it's coming from a higher degree polynomial. What's the degree of this polynomial? Is 6, right? Because we got 2 from this one. If you multiply that out, that's x squared. Multiply this out, it's going to be 8x to the third, and then times another x. So squared, third power, and then one more is 6th power. So from Algebra 2, what do we remember about degree and number of zeros? Yeah, whatever the degree is, that's how many solutions we have. So how many do I have here? Only 3. That brings up the idea of them counting more than once. Multiplicity. Y'all remember that word? That came up with Algebra 2. So we talk about multiplicity. X minus 2. How many times is x minus 2 a factor of this polynomial? Once. So it counts one time. Anytime it counts one time, that means it's going to cross the x-axis at that point, at 2. If we graph this polynomial, we'll see that happen. This one counts how many times? Twice. So it has a multiplicity of 2. So a multiplicity of 2 touches the x-axis. And I think the word that I used a lot in Algebra 2 was bounce. It bounces off the x-axis. Go back to the graph of example F, and we had that squared factor, and it, at -3, and it bounced off the x-axis there. That's what's happening. What's the multiplicity of 3 over 2? Multiplicity of 3. And that's going to cross the x-axis. Multiplicity of 3. What's the multiplicity of 2? 1. Okay, so the relationship is odd multiplicity what's it going to do to the x-axis? It's going to cross. Even multiplicity, it's going to touch or bounce. Yeah. All things that we talked about in Algebra 2, no matter what semester you had it. If you had it last semester, it's pretty fresh. You had it last year. Maybe it's not as fresh, but we did talk about it at some point with that. So very, very much a review section. We just put more of it together. This was probably a whole week of stuff in Algebra 2. We're doing it all in one day. that kind of stuff. All right. Now, so factored form, set each factor equal to 0. Look at the exponent that's on the factor. That gets you your multiplicity. Always. Same thing. And then knowing what the graph is going to do. If it's an even multiplicity, then that's going to touch the x-axis. If it's an odd multiplicity, it's going to cross. You can find those things without graphing the polynomial. What happens is they'll throw polynomials to you that if you graph them on your graphing calculator, they're so large you can't see what's happening. Okay, that your calculator, you can zoom out a whole lot, but you really can't see what's happening to see the graph. So you got to know this information, and it's kind of a theory idea. All right. Next, turning points. So turning points are how many times the graph changes directions. That's all it means. Okay. So turning points are the change in direction of the graph. We're not finding exactly how many, where the turning points are. We're just finding how many there are, or how many there could be. Finding exactly where they're happening at is a calculus idea. It involves taking a derivative. If you end up taking pre-cal, toward the end of pre-cal, you'll do like a miniature calculus introduction. You'll start taking derivatives. And finding those turning points can be done with a derivative of a polynomial or a function. But we're not concerned about finding them. We just need to know how many there could be for that. And it's really easy formula. Take the degree of your polynomial, subtract 1. That tells you how many turning points there could be. Doesn't tell me that there are exactly that many. Just means there could be that many. So for this polynomial, example I there, f of x is equal to x cubed plus 3x squared minus 5x plus 4. All we got to do is find the degree. What's the degree of that polynomial? 3. So how many turning points can we have? 2. 3 minus 1 is 2. N minus 1 is our formula. So we're going to do 3 minus 1 is 2 turning points. And if you think about the graph of a cubic, those turning points happen at that spot and that spot. It doesn't mean there is going to be 2 every time it's a cubic, because sometimes we could do a cubic and it not have those big peaks and valleys. Maybe a cubic that does that. That's still cubic, but it's only got 1 turning point. But it could possibly have 2 turning points on that. So turning points, we're finding the possible maximum number of turning points, not exactly what those turning points are. Again, got to have a little calculus to find exactly. We could find, what's another name for those peaks and valleys that we talked about maybe in chapter 3? Local maxes and mins is where those are happening at. In calculus, there's some good algebra ways to find those exact numbers there. We have to inspect the graph to get, but calculus, there's a good algebra way to do that. So it's pretty neat. Okay, let's look at another one. Not so nice to us here. It's not in standard form. Standard form is super easy, so we can't do a lot of stuff in standard form because it's too easy. So what do we need in order to determine the number of the maximum number of turning points? We need the degree. What's the degree? 4th degree. So the maximum number of turning points would be 3. On the quiz, everybody ought to get every one of those right. It's too easy, okay? I'll put like 7 of those on the quiz and then 3 real problems. No, I won't do that. That's a good idea. Too bad it won't happen. All right. Now, something that's a little bit more merit here. And the last thing of this section is forming a polynomial in standard form, given some information about that polynomial. Okay. So they're telling us on this one, they're telling us the zeros and what degree we should be going for. Okay. The zeros are 1, -2, and 3, and they want us to form a polynomial and write it in standard form that has a degree 3 and has those 3 zeros. So, what would, they're zeros, that means they're what? What else is another name for that? X-intercepts, and x-intercepts come from what part of a polynomial? The factors. So we just need to get the factors that go with those 3 zeros. What's the factor that goes with 1? X minus 1. What's the factor that goes with negative 2? X plus 2. And then the last one, X minus 3. Okay. So changes the sign, gets us that factor. To get it in standard form, what do we need to do to that? Multiply it out. So got to do a little bit of algebra 1 here. So pick your 2 favorite ones to multiply together first. It doesn't matter which 2. I'm going to pick these last 2 here, and then multiply that answer by the x plus or the x minus 1. Okay, so I'm going to multiply these 2 out. It'll be x squared minus x minus 6. And then I'm going to multiply that by x minus 1. That'd be x to the 3rd power minus x squared minus 6x. And then distribute the minus 1. So that'd be another minus x squared plus x plus 6. And then combine like terms. X cubed minus 2x squared minus 5x plus 6. How can I check to make sure that's right? Okay, so if I graph that, what should the graph do? It should go through the x-axis at 1, -2, and 3. Okay, so if I graph that, clear that one out, x to the 3rd power minus 2x squared minus 5x plus 6. There's the -2, 1, and 3. So it's crossing at the right places. Not very likely that I could make a mistake and it do the right things. Okay, so be careful of that. Okay, that's easy enough. It's doing a little harder. -3 with multiplicity of 2, that's what that means there. -3 has a multiplicity of 2 and 5, and the polynomial has degree 3. So what's our factored form look like? X plus 3 squared. Good job. If we're going for standard form, we got to multiply all this out. So I'm going to square the x plus 3 first. And if you need to write that out and do your distributive property, by all means do that. I've done enough of that, and some of y'all have that in your pocket. And then we're just going to distribute from there. X to the 3rd plus 6x squared plus 9x. And then distribute the minus 5. So that'd be minus 5x squared minus 30x minus 45. And then x cubed plus x squared minus 21x minus 45. We built the polynomial as described. Again, same things we did in Algebra 2, but we took about a week to do all of those things. and we're doing it in one lesson in college algebra. So a lot of the same stuff, things you have experience with, and going from there. So here's the kind of preliminary plan